Hi everyone, hope you all are doing well. Today's topic is JavaScript's execution context. Many of you have repeatedly requested me to make a video on this topic in the comment section of my channel. I hadn't responded for quite some time and there was a reason behind that. I wanted to make sure we first covered the fundamental concepts of JavaScript before diving deep into execution context. There's another reason too. Once you finish watching today's video, you will realize that many of the topics we discussed earlier, like scope, hoisting, and closures, will start making much more sense and feel newly discovered from a deeper perspective. We already have a preliminary idea about these topics, especially if you have been following my videos on this channel. So today, through the lens of context, we are going to rediscover all those concepts by understanding execution context in a completely new way. And by the end, you will finally understand how everything connects together, how two hands make four. So, without wasting any more time, let's get started. Before diving into JavaScript context, let's take a step back and see how JavaScript actually runs, whether in a browser or in a terminal. You might be wondering why I'm mentioning the terminal. Well, that's because JavaScript now also runs outside the browser through Node.js. So, let's first explore how that happens behind the scenes. So, the code you write in JavaScript, when it reaches the browser, or in the case of Node.js, the server, it's ultimately executed by the computer. But here's the thing. Computers don't understand JavaScript. They only understand binary or machine language. So, somehow, the browser has to translate our JavaScript code into machine language so that the computer can actually run it. That means there must be some kind of mechanism inside the browser or in the Node.js runtime that performs this translation from our programming language to machine language, right? Exactly. That mechanism inside the browser is called the JavaScript engine. In Google Chrome, this engine is known as the V8 engine. Other browsers use their own engines. Firefox uses SpiderMonkey, Internet Explorer uses Chakra, and Safari uses JavaScript Core. No matter which engine it is, every browser has one, and they all perform the same code task, converting our JavaScript code into machine language. Different browsers may implement this process in their own way, but all of them follow the same standard, known as the ECMAScript specification. ECMAScript is basically the official standard that defines how JavaScript should work, like ES5, ES6, and so on. Since each browser's engine implements the standard slightly differently, sometimes the same piece of code may produce slightly different outputs in different browsers. Anyway, once our code reaches the browser, it's handed over to the browser's JavaScript engine. The engine then converts that code into machine language, which the computer can finally understand. And that's how we get to see the output displayed on our screen. So that's the overall top-level view of how JavaScript code runs. Now, as programmers, we don't really need to understand what happens at the hardware level because our focus isn't building hardware. We are application developers. What truly matters for us as JavaScript developers is understanding what happens inside the engine when it runs our code. In other words, we need a clear picture of how the JavaScript engine actually compiles and executes our code. That's the foundation of everything. So let's start right there. But before we do, there's one important thing I should mention. I have been talking mostly about browsers. So you might be wondering what happens in the case of Node.js? Well, Node.js actually uses the same V8 engine that powers Google Chrome. Ryan Dahl, the creator of Node.js, is a truly brilliant programmer. What he did was take Chrome's V8 engine, which was already built, tested, and extremely fast, and use it outside the browser. V8 is one of the most powerful and highly optimized compilers in the existence. It converts JavaScript into machine language with incredible speed and efficiency. That's why Google Chrome performs so well, because of the V8 engine. Ryan Dahl realized that V8 was already the best engine out there. So he thought if he could extract it and use it outside the browser, he wouldn't need to build a new engine from scratch. The compilation part would already be handled by V8. Since V8 was written in C++, Ryan integrated it directly into his own C++ program. In other words, his C++ code and the V8 engine were combined, and that's how the Node.js runtime was created. Now, let's take a look at what actually happens inside a JavaScript engine when it compiles JavaScript code. To understand that, we need to start with a bit of history. When JavaScript was first introduced, it was an interpreted language. meaning there was no compilation process. There wasn't a compiler to convert JavaScript into efficient machine-level code. And here we come across two important terms, interpretation and compilation. At first, interpretation and compilation might sound like the same thing because both convert our code into machine code, right? That's true in essence, but the way they work is completely different. Let's take a closer look at the difference between interpretation and compilation. Here, we have some JavaScript code written by us. This code is readable to humans, but the computer doesn't understand it. So what does a computer understand? It only understands binary, zeros and ones. That's machine language, and while the computer understands it perfectly, we humans can't read it. So our job is to take the human-readable JavaScript code and convert it into machine code, so the computer can understand what we are asking it to do. There are three main ways to perform this conversion: interpretation, compilation, and the number three is a hybrid approach, a mixture of both. Back in the 90s, JavaScript used to be a purely interpreted language. But in recent times, modern JavaScript engines use a combination of both interpretation and compilation to translate code into machine language. The language itself hasn't changed. It's still that JavaScript, but the way it's implemented has evolved dramatically. Now let's see how an interpreter actually works. How JavaScript code gets converted into machine code through interpretation. Inside the interpreter, there's already a set of equivalent machine instructions for every command or expression we write. For example, look at this piece of JavaScript code. It contains several lines of instructions. The interpreter already knows the corresponding machine-level operations for each of these lines. Suppose we have a variable where two numbers are being added. That's an arithmetic operation. Then, in the next line, there's a console log statement that prints something on the screen. And there could be many more such instructions in our code. For every one of these, the interpreter has a predefined binary or machine code equivalent, which tells the computer exactly how to execute that particular command. So, we can visualize it like this. When we run a program, the interpreter starts executing the instructions line by line. First, it looks at the first line, where two numbers are being added. The interpreter already knows how to handle that operation. So it takes that instruction, translates it into binary, and executes it. Once the first line is done, it moves to the next line. Let's say that's a console log statement. The interpreter knows how to execute that too, so it runs it. Then it moves to the next line, and the next, and so on. But there's a problem. This process is quite slow because the interpreter has to execute one line at a time, constantly going back and forth between reading the script and executing it. This repeated process makes pure interpretation significantly slower. That's why JavaScript was very slow back in the 90s. However, this process did have one big advantage. You might wonder, if it was so slow, why was it designed this way? The reason is that JavaScript was very easy to debug at that time. Here's why. The interpreter executes one instruction at a time. So, if it encounters an error while running any particular line, it can immediately stop and notify the programmer exactly where the problem occurred. This made debugging much easier because developers could instantly identify the issue, fix it, and continue running the code. So, the advantage of interpretation was that it was easy to debug, but the downside was that it was slow. To overcome that slowness, the concept of compilation was introduced. Let's now see how compilation works. A compiler works differently. Instead of executing code line by line, it takes the entire program at once, translates the whole thing into machine code, and then runs it line by line from that compiled version. This makes the process much faster compared to interpretation. However, there's a problem here too. Suppose there's an error in one of the lines of code. The compiler won't stop there. It will continue compiling the rest of the code. That means if your program contains any malicious or faulty logic, for example, an infinite loop or a piece of code that causes a memory leak, it might still get executed and potentially crash your system. You won't have the chance to stop it midway like in the interpreter's case. So that's the major drawback of compiled languages. They can crash the system and are harder to debug. Why? Because the entire code gets compiled first, so we don't immediately know which exact line contains the error or bug. To find that out, we have to run the program first, and only then can we detect where the problem is. In short, with interpretation, we had the advantage of easy debugging but slower execution. On the other hand, compilation gives us speed, but makes debugging difficult and increases the risk of system crashes. So imagine if there were a way to combine both, to get the best of both worlds, fast execution and easy debugging. That's exactly what Google Chrome did in 2008 when they introduced the V8 engine. They combined these two approaches into a single system and called it a just-in-time compiler or JIT compiler. This JIT compiler merges the easy debugging nature of interpretation with the high-speed execution of compilation, creating a highly optimized and balanced process. This approach might not be as fast as fully compiled language, but it's definitely fast enough that users can't tell the difference in real-world performance. Now, let's see how the JIT compiler actually works. In JIT, the just-in-time part behaves like an interpreter. It reads the code, while the compiler part translates it into machine code. Here's what happens. When we write our JavaScript code, the JIT compiler doesn't immediately compile the entire thing. Instead, it keeps the code as it is. When a particular function or instruction is invoked, say, for example, the instruction 1 function, the JIT compiler instantly compiles that specific function into machine code, executes it, and returns the result. Now, suppose we call another function, instruction 2, and an error occurs inside it. The JIT compiler would immediately detect it and say, I have just in time compiled this function, and there's an error here. Stop right there. This allows the programmer to instantly see where the issue is and fix it, maintaining both speed and debugging flexibility. That means we can still debug easily, so it's both easy to debug and fast enough to run efficiently. In other words, it's truly the best of both worlds. That's the core feature of the JIT compiler, and this is exactly how modern JavaScript engines, including Node.js, work today. They compile JavaScript through just-in-time compilation. I hope this part is clear to you. So, with that understanding, let's move on to today's main topic, JavaScript's execution context. Many people start learning directly from execution context, but I personally believe it's important to first understand how the compilation process actually works. Now that you have that foundation, when we dive into execution context, your brain will be able to connect both parts and visualize the complete picture of how JavaScript truly operates. So, let's move on to our main topic, JavaScript execution context. In my opinion, execution context is the most important concept in JavaScript. The reason is simple. If you truly understand how it works, then advanced topics like hoisting, scope chain, and closures will become incredibly easy to grasp. Let's start by thinking about how we usually write code. One common strategy is to break our code into smaller parts. These separate pieces of code can have different names, like functions, modules, or packages. But no matter what we call them, their purpose is the same, to break a complex program into smaller, more manageable chunks. This division reduces complexity and makes our code easier to read, maintain, and debug. On the screen, we can see an example. On the left side, there's a block of code, and on the right side, the same code is divided into smaller functions. At first glance, the code on the left might look simpler, but if you look closely, it's not really practical. In this example, I have represented each action with a simple console log statement, just for easy understanding. But in a real-world application, things aren't that simple, right? Instead of just console logs, there would be complex logic, multiple algorithms, API calls, and data processing happening behind the scenes. Now imagine if we wrote all those complex operations, like taking orders, processing them, and completing them, all inside a single file or function. That would make our code neither easy to read nor easy to maintain. It would quickly become messy and difficult to debug. But if I break each task into smaller functions like the ones on the right side, it becomes much easier to maintain and the overall complexity of the code decreases significantly. In the same way, JavaScript also breaks down our code into smaller parts before interpreting it. This helps reduce the complexity of execution. Each of these smaller units is what we call an execution context. That's the simplest definition you can think of. An execution context is basically a small, isolated environment where a specific piece of code is interpreted and converted into machine language. So, to make its job easier, the JavaScript engine divides our code into smaller parts and executes them one by one. Each of those parts is an execution context. In today's session, we won't be writing any code. Instead, I will walk you through how execution contexts are actually created inside the JavaScript engine, line by line, so you can clearly visualize what happens behind the scenes when your code runs. Let's imagine the left side of the screen is our code editor, where we will be writing the code, and the right side will show how the execution context is created. Now, at this point, the left side, our code editor, is completely empty. Even when there's no code written yet, JavaScript still creates something called a global execution context right at the very beginning. So, what exactly is this global execution context? Think of it as a simple object, or you can visualize it as a box, a container that holds everything your program needs to start running. At the very start, before any code is executed, this global execution context is created. Inside it, the first thing we have is the window object, which I'm sure you are already familiar with. Next, we have the this keyword, which initially points to the window object. Then comes the variable object. And finally, another structure called the scope chain. There's one more important thing to understand. The global execution context actually goes through two distinct phases. When the program runs for the very first time, it enters what's called the loading phase or creation phase. During this phase, your code doesn't execute yet. To summarize, when the global execution context is first created, it contains four main components: window, this, variable object, and scope chain. And before any line of code runs, JavaScript first goes through the loading phase. Now, let's assume we have written some code. It's just a short 7-line script where we have a variable named topic and a function called getTopic that simply returns that topic. As we have just discussed, when the global execution context is created, it already includes window, this, variable object, and scope chain. Along with that, during the loading phase, any functions and variables declared in our code, like topic and getTopic, also get added to the global execution context. But here's an important point. During the loading phase, these variables and functions are only recognized, not yet fully executed. That means their values are temporarily set to undefined until the actual execution begins. As I mentioned earlier, there's something inside the global execution context called the variable object. During the loading phase, JavaScript allocates a specific space in memory for every variable declared in the code. So, for example, a memory slot is created for our variable topic, and JavaScript assigns it the value undefined at this stage. Similarly, the getTopic function is also stored inside that same variable object. But instead of assigning it as undefined value, JavaScript stores a reference to the function, meaning the function's entire structure or body is saved somewhere in memory. So now, through the global execution context, JavaScript already knows that there's a function called getTopic defined in the program. It hasn't executed it yet, but it's aware that such a function exists and might need to be called later during execution. Once the creation phase is complete, JavaScript moves on to the second phase, the execution phase. In this phase, the program starts running from the very beginning, line by line. So, when execution begins, it looks at the first line, var topic is equal to JavaScript execution context. Now, JavaScript already knows the variable named topic because during the loading phase, it had already stored it in memory with the value undefined. When the execution phase starts, JavaScript simply replaces that undefined with the actual value we have assigned. This is the first time the code truly gets executed. During the creation phase, JavaScript also stored the getTopic function in its memory. It knows that somewhere in this program, there's a function called getTopic. So when it reaches line 7, where the function is called, it retrieves that function reference from memory and executes it. Now imagine we write console.log topic at the very top of our code, meaning we are trying to use the variable before it's even declared. In earlier tutorials on JavaScript hoisting, I explained this concept, but not in this much detail, not in the context of the execution context. Back then, I said that during hoisting, JavaScript conceptually moves all the variable declarations to the top of the scope, though only the declarations, not the actual values. But now, through the lens of the execution context, you will understand what really happens behind the scenes. As we saw earlier, during the loading phase, JavaScript already stored the variable topic in memory and assigned it the default value undefined. That's why when we try to print topic in the very first line before its declaration, the console will show undefined, which is the value set during the loading phase. Then, when the program enters the execution phase and reaches the line var topic is equal to JavaScript execution context, if we place our console log after that line, we will see the correct value, right? That's because during execution, when JavaScript encounters this line, it updates the value of the topic variable in the execution context from undefined to JavaScript execution context. Since the value is now updated, any console log that runs after this point will display the correct value. So, if you have watched my earlier tutorial on hoisting and now you are watching this video, you will finally understand why this hoisting behavior happens inside the JavaScript engine. In that tutorial, I explained hoisting as variables being moved to the top, which was just a simplified way to help you visualize it. But now, through execution context, you can see what actually happens behind the scenes. I hope this part is crystal clear now. To summarize, the global execution context is basically a JavaScript object. At the very beginning, it contains the window object if we are in a browser environment, or the global object if it's Node.js. There's also a this object that points to the same window or global. Then, all the variables declared in our code are stored inside something called the variable object. And any functions we define are also stored there, but only as references, meaning JavaScript just keeps a pointer to their full body in memory. Then, when the program enters the execution phase and reaches the line var topic is equal to JavaScript execution context, if we place our console log after that line, we will see the correct value, right? It also keeps something called a scope chain. As we know, JavaScript uses lexical scoping, meaning each function knows exactly where it was written and can access variables from its outer scopes. So, JavaScript maintains all these scopes together inside the scope chain. That was the visual representation of the global execution context. Now, let's go a bit deeper. By this point, you have already understood how the global execution context works. The good news is that after this, you only need to understand one more type of execution context, the function execution context. And the interesting thing is, it's almost identical to the global execution context. The only difference is that it's created every time a function is called. Let's quickly recall what happened inside the global execution context. It created a global object, created a this object, allocated memory for variables and functions, and initially assigned all variables the value undefined, right? Now, if you think carefully, which of these 4 steps do you think won't be necessary when a function gets executed? Exactly, the global object shouldn't be created again inside a function execution context, because the entire program already has one global object that was created earlier, and all functions can access it when needed. So, instead of creating a new global object, something new happens inside the function execution context. It creates an arguments object. This object holds all the parameters passed to that function. That means whenever we define a function in JavaScript and it has parameters, JavaScript automatically creates an object called arguments inside that function's execution context to store those values. If we write console.log arguments inside the function body, you will see all the past parameters neatly stored as key value pairs within that arguments object. So, the only structural difference between the function execution context and the global execution context is this: the global one contains a global object, while the function one contains an arguments object. Everything else remains exactly the same. Simply put, think of the global execution context as an entire world. Whenever we call a function, a new world is created inside that global world, following the same structure and behavior. I hope that makes the idea clear. When a function is called, JavaScript creates a completely separate execution context for it. Inside that context, it builds an arguments object to hold all the parameters, creates a this object as usual, and allocates memory for all the variables and inner functions defined inside that function. That means hoisting also applies inside functions. During the creation phase, JavaScript will assign undefined to all variables within that function. And that's exactly why hoisting happens there too. And this is how the function execution context works. Now, remember how we said that in JavaScript, one function can contain another function? That means there can be multiple execution contexts. The global execution context is always there, and alongside it, multiple function execution contexts can be created as different functions are called. So, obviously, JavaScript needs a way to keep track of all these contexts somewhere. And since JavaScript is a single-threaded language, meaning everything runs on one main thread, that same thread is also responsible for managing all these execution contexts, creating them, stacking them, and clearing them one by one. JavaScript actually stores these contexts one on top of another, just like a stack. And this stacking structure is called the execution stack, or more commonly, the call stack. At the very beginning, JavaScript places the global execution context at the bottom of the stack. Then, whenever a function is called, a new function execution context is created and pushed on top of it. If that function calls another function inside it, another context is stacked above that, and so on. In this way, JavaScript keeps adding and removing execution contexts in a stacked order as the program runs. So now we have a complete picture of what an execution context really is. It's made up of two types, the global execution context, the function execution context. Now, let's move on to something a bit more advanced. So far, we have only seen how the execution context works in the global scope or when a function is called directly from the global scope. But what if we have multiple functions? Or if one function contains another function, in other words, nested functions? How does the execution context behave then? Because every time JavaScript creates an execution context, it needs to keep track of them somewhere in memory. There has to be some logic to determine which context should run first and which one should execute next. To manage all of that, JavaScript needs to maintain a specific data structure, right? And that data structure is called the execution stack. It's actually based on a stacked data structure. Think of it like stacking books on a shelf. You place one book on top of another. Similarly, JavaScript stacks each execution context on top of the previous one inside the execution stack. Now, a stack has one special property. The last item that goes in is always the first one to come out. In short, it follows the LIFO rule. That means last in, first out. Alright, let's connect this idea with our code. We know that whenever we run a JavaScript program, the global execution context is created first. Whether our file contains code or not, this global context will always be created automatically. And once it's created, JavaScript places this global execution context at the very bottom of the execution stack. That's where everything begins. Next, let's look at our code. Inside it, we have three things. A variable declared with var a function called one with its definition, and finally a call or invocation of that function. These three, the variable a, the function one, and its invocation, all exist in the global scope or the root level of the program. Inside the body of the one function, there's another nested function called two, and inside two, there's yet another function called three. These nested functions are not part of the global scope. They belong to their respective inner scopes. So, during the creation phase, JavaScript stores the variable a with the initial value undefined and registers the body of the function 1 with the variable object. Since there's nothing else in the global scope, JavaScript then moves on to the execution phase. In this phase, execution starts line by line. First, it updates the value of a from undefined to 1. Then it moves to the next line, where it finds the function definition of 1. Since that function's reference is already stored in the variable object, JavaScript skips over the function body for now and continues to the next line, the point where 1 is actually invoked. As soon as the 1 function is invoked, JavaScript creates a brand new function execution context inside the execution stack, placed right above the global execution context. When this new context for 1 is created, it first enters its loading phase. Since the 1 function doesn't take any arguments, the arguments object inside this execution context will remain empty. Then comes the this reference, which points to the global object, in this case, the window object. After that, we have the scope chain and the variable object. Inside the variable object, there's only the to function. Why? Because inside the body of 1, there are no local variables declared, only a console log statement that tries to print a. But since the variable a is not defined inside 1, it doesn't appear in this context's variable object. Instead, JavaScript will later look for it in the outer scope using the scope chain. However, the one function body does contain another function declaration, the to function. So, during the loading phase, JavaScript stores that to function inside the variable object, just like it stored the function definitions earlier in the global execution context. It follows the exact same process, only this time it's happening inside the function's own scope. Alright, now let's check if there's anything else inside the body of one function that needs to be added to its variable object. The answer is no. There's nothing else. So next, JavaScript moves to the execution phase. And just like in the global execution context, it starts executing line by line. The first line inside the one function is console log A. At this point, JavaScript checks whether the variable A exists inside the variable object of the current execution context. It looks and finds nothing. Since the variable A isn't declared inside the one function, JavaScript moves to the next step. It follows the scope chain to look into its parent scope. Now, what's inside the parent scope? Yes, the variable A is there, defined in the global execution context. So, JavaScript retrieves that value and prints it in the console. It's important to clearly understand one thing here. The scope chain is essentially a lexical environment. This means every scope is connected to its parent scope in a linked structure. The term chain is used because each scope holds a reference to its parent or ancestor scopes, forming an actual chain-like connection. That's why when JavaScript couldn't find the variable A in the one function's own variable object, it followed that chain upward to its parent or ancestor scopes and successfully found A in the global scope. Hopefully, that part is clear. Now let's go back to the code flow again. After printing the value of A, the program moves to the next line. There it finds the body of the to function. But at this stage, JavaScript doesn't need to do anything with it because during the loading phase, the reference to has already been stored in memory. So it skips over the function body and moves to the next line where it sees that to is being invoked. Since the to function is now being called, JavaScript creates a brand new function execution context for it and places it on top of the execution stack. Just like before, when this new to execution context is created, it first goes through its loading phase. During this phase, it populates its scope chain, meaning it links itself with the variable objects of its parents or ancestor scopes. Inside the body of to, there's a variable named b. So in this new context variable object, JavaScript stores b with the initial value undefined. Then it finds another function definition, 3. So just like before, JavaScript stores the reference to the 3 function inside the variable object of to. Then in the next line, the program moves to where the function 3 is called. Since it's still in the loading phase, there's nothing to execute yet. That part is done. So now it enters the execution phase and starts running each line one by one. Inside function 3, what's the first line? It's a console log of the variable b, but that variable hasn't been initialized yet. In this context, its value is still undefined. So when the program runs that line, it prints undefined. Now, you can clearly see why during hoisting, variables often print undefined. Once you understand how the execution contexts work, many other tricky behaviors of JavaScript starts to make sense. So, pay close attention and try to grasp these terms deeply. Alright, after that, in the next line, the variable's value is being assigned. So the value of b changes from undefined to 2. Then in the following line, we see the definition of the 3 function. The execution context doesn't need to do anything here. So it simply skips over this line. The next line shows that the 3 function is being invoked. And not just that, it's being called with an argument 4. Since the 3 function has been invoked, a brand new execution context is created inside the execution stack. Now pay close attention here. During the loading phase of the 3 execution context, we can already see that there's a value inside the arguments. At index 0, it's 4. That's because when the function was called, the value 4 was passed in. And here's something interesting. Look at how we named the parameter inside the 3 function. It's called d, right? So during the loading phase itself, a variable named d appears inside the context, and it's already assigned the value 4. Then it moves to the next line. There's a console log statement. Nothing special happens there yet. After that, we have let c is equal to 3, and this is where things get a bit different. You see, although var, let, and const are all used to declare variables, their behaviors are not the same. For var, during the loading phase, JavaScript automatically allocates memory and sets its value to undefined. But for let and const, JavaScript still allocates memory during the loading phase. The difference is they remain inside what's called the Temporal Dead Zone or TDZ until the actual line of code where they are declared is reached. That means even though they exist inside the execution context, they can't be accessed through the variable object yet. Now, you might wonder what exactly is the temporal dead zone? It's the period between a variable being created in memory and being initialized with a value. During this time, the variable technically exists, but since no value has been assigned, JavaScript keeps it temporarily inaccessible. If you try to access that variable during the TDZ, you will immediately get a reference error. In simple terms, the program knows that the variable exists, but it's not ready to be used yet. And until the code execution reaches that specific declaration line, you won't be able to access it from the variable object either. You can think of it like an iPhone's locked screen. The phone is there, but until you enter the PIN and unlock it, you can't do anything with it. Now, many people wonder, doesn't the same thing happen with var? Why does JavaScript assign undefined to variables declared with var but keeps let and const inside the TDZ instead of doing the same? Excellent question. The main reason is that var comes from the older versions of JavaScript, especially ES5 and earlier, where there was no concept of safety checks or the temporal dead zone. Back then, JavaScript didn't want the program to crash if a variable was accessed before initialization. So, to avoid breaking the program, it would automatically assign undefined as a fallback value, just try to be a bit more smart. But let and const were introduced in ES6, where the goal was to keep the language safer and more predictable. If JavaScript had assigned undefined to them as well, it would have created the illusion that the variable was properly initialized, even though it wasn't. So, JavaScript intentionally blocks access to those variables during that time to signal to developers. The variable exists, but it's not ready to be used yet. Hope that clears things up. Now let's get back to our flow. At this point, inside the tree function, there's nothing else left to load, so it moves to the execution phase. In the first line, we have a console log printing c plus d. We already know that the value of d is 4, but the variable c is still inside the temporal dead zone, meaning it can't be accessed yet. So this line will throw a reference error because the program can't reference c from memory at that point. However, if we had written the code the other way around, first declaring let c is equal to 3 and then logging it in the next line, the behavior would have been completely different. In that case, during the creation phase, c would still start in the dead zone. But by the time the execution reached that line, its value would already be assigned. Then, when the console log ran, both C and D would be accessible and their values would print correctly. Clear now? So you can see how JavaScript actually works behind the scenes. We have also learned how hoisting truly operates at a machine level through the concept of the execution context. Alright, now let's move forward. Inside the tree function, once the console log runs successfully, it will print 7. After that, is there anything else left in the function? No, there isn't. Since there are no more lines to execute, the work of the tree function is complete. And whenever a function finishes its job, it immediately gets popped out from the execution stack. That means, since the tree function has finished executing, it will be removed from the stack following the LIFO. That means last in, first out rule. Now, who's at the top of the stack? The to function. If we check the body of to, do we see any remaining lines to execute? No, it's done 2. So, 2 will also exit from the execution stack. Finally, since there's nothing left to run in 1, that function will also pop out, leaving the execution stack completely empty. Since there are no more functions left to execute, the global execution context will also exit from the execution stack. However, if there had been more code to run in the global scope, for example, another function called write after 1, then the global execution context wouldn't have been removed yet. Instead, it would have continued executing the next function just like before. I hope by now you have no doubts left about execution context. While learning about it, we also discovered how hoisting actually works, didn't we? Now, let's move on to another important concept, scope. We have already discussed scope before, but this time we will understand how scope works in relation to the execution context. Take a look at this simple example. Here we have a function called hello. Inside it, there's a variable named message declared with var, which holds a certain value. Outside the function, that is in the global scope, we are calling or invoking the hello function. And in the next line, we are trying to print the message variable using console log. It's a very simple setup. So, based on everything we have learned so far, what will happen if we run this program? First, the global execution context will go through its creation phase. During this phase, it will find a function named hello and store its reference inside the variable object. Once that's done, there's nothing else left for the creation phase, right? Perfect. Now the execution phase begins. The first line is the definition of the hello function. Since we are in the execution phase, there's nothing to execute here. The function's reference is already stored in memory. So the program moves on to the next statement, where the hello function is invoked. As soon as that happens, a new execution context for the hello function is created. Inside the creation phase of the hello function's execution context, the variable message is placed inside the variable object with the value undefined. Once the creation phase is complete, the program moves to the execution phase, where the variable message gets its actual assigned value instead of undefined. So, in the execution phase, the value of the message variable becomes hello world. After that, does the hello function have anything else to do? No, it doesn't. So the hello function's execution context will now be popped off or destroyed. That means the program returns to the global execution context. Now, what happens next? After the hello function is invoked, the next line is console.log message. So the program will now try to print message. But wait, is the message variable declared inside the global execution context's variable object? No, it isn't. That variable was created inside the function execution context. And when that function finished executing, its execution context, along with its scope chain and variable object, was completely removed from memory. That's why when the console tries to access message, JavaScript throws a reference error. Can you relate this now? Those of you who have seen my video on scope might remember the example I gave. A child can always access or inherit things from its parent, but a parent can never access what belongs to the child. Back then, it was just an example, but now you can actually visualize how the program manages all of this behind the scenes. That means, while understanding execution context, we have rediscovered the concept of scope in a much clearer and more practical way. Now, let's move on to another very important topic, closure. Just like we visualized execution context earlier, we will now see how a closure is created and how it works step by step. First, the program creates the global execution context. We are now in the creation phase. During this phase, the program scans through the code and finds a variable named sum and a function named doSum. So, memory is allocated for sum and its initial value is set to undefined. The entire function definition of doSum is stored in memory as a reference. Once the creation phase is complete, the execution phase begins. In the execution phase, the first line sets sum is equal to 0. Next, the program skips over the doSum function since it's only a definition. Then it moves to the line var temp is equal to doSum in the bracket 2. Here the function is being called, so a brand new function execution context is created for doSum. Now, the creation phase of that function execution context begins. The parameter a receives the value 2. So in memory, we have a is equal to 2. Inside the function, there's an anonymous function being returned. That function's reference also gets stored in memory. Once the creation phase is done, the execution phase starts. During this execution phase, the doSum function doesn't perform any calculation. Instead, it simply returns that anonymous function. When that happens, the doSum execution context is popped off the stack. But something very important also occurs at that exact moment. A closure is created. Why does that happen? Because when the anonymous function is returned, it still remembers the data from its outer scope. In this case, a is equal to 2. Even though the doSum function itself gets destroyed, its lexical environment doesn't disappear completely. JavaScript realizes that this inner function might be called again later, and when that happens, it will need access to those outer variables. So, it preserves that environment in a separate structure called the closure scope. Now you can understand JavaScript is really smart. Next, the code moves to the line sum is equal to sum plus temp8. Here, the function is called again, meaning temp8 is invoked. This creates a new execution context for the anonymous function. During its creation phase, the parameter b is assigned the value 8. When the execution phase begins, the function executes return a plus b. Now, since a doesn't exist in the current scope, JavaScript follows the scope chain and looks into the outer scope, which is the closure scope. There it finds a is equal to 2, performs the calculation, 2 plus 8 is equal to 10, and returns the result 10. At that point, the temp function's execution context completes its job and gets popped off from the stack. So, in the line sum is equal to sum plus temp 8, the value of sum was initially 0. That means it becomes sum is equal to 0 plus 10. Now, where did that 10 come from? It came from the temp function's execution context. Now you can clearly see how a closure actually works. A closure is basically a mechanism that keeps a function connected to its outer environment, even after the outer function has been destroyed. This is one of JavaScript's most magical yet completely logical behaviors, and it all originates from the concept of the execution context itself. So, everything you have seen so far, this is what JavaScript's execution context truly is. By understanding just this one topic, we have been able to uncover how JavaScript actually works behind the scenes. We discovered how scopes are formed and how confusing topics like closure and hoisting are really operate logically within the language. All this time, we used to just repeat what we heard, that hoisting means variables are lifted to the top and closure means a function stays connected to its outer environment. But after watching this video, you should now have a clear, inside-out understanding of how and why JavaScript behaves this way. From today, you may not understand your wife, but you will definitely understand JavaScript. I have given my best effort to explain this topic as clearly as possible. If this video helped you understand these concepts better, please don't forget to like and comment. It truly encourages me to keep making more videos like this. And if you have any valuable feedback or specific topics you would like me to cover next, feel free to let me know. Your small words of motivation inspire me to keep creating and sharing more. Thank you so much for everything and thank you so much for watching my videos. I will see you again in another one.